Good day, ladies and gentlemen. My name is Michael Odidi. I am a PhD student under the SIBA Research Group at the University of Cape Town, and I hope you enjoy my presentation. The title of my presentation is The Effect of Bed and Fluid Properties on Capillary Pressure and its Impact on the Hydrodynamic Modeling of Heap Leaching Systems. Heap leaching begins with your run-of-mine ore, which is then crushed, agglomerated, and stacked in order to form a heap. The heap is then irrigated with a lixiviant solution that percolates through the heap, dissolving the targeted metal species, and is collected in a pregnant leach solution pond. The solution from this pond is sent to a metals recovery unit, in which the targeted metal is stripped, producing your barren leach solution that is recycled back to the top of your heap, together with the addition of fresh lixiviant. Now, heap leaching has the following advantages. It is economically viable in the treatment of low-grade ore. It has been used to recover a variety of base and precious metals, and it is a process that is gaining popularity due to the depletion of high-grade ore reserves around the world. The disadvantages of this process, though, is long extraction times, lower than expected recoveries, and in certain cases, high operational costs. One of the major problems that have been identified is preferential flow. To take you through what it means, upon irrigation of your heap, what one would like is to have a uniform distribution of solution, as this leads to optimized recoveries. However, in reality, what tends to happen is that sections of your heap receive high velocities of fluid flow, while other sections receive little to no fluid contact. One of the factors linked to this is capillary pressure, which is a suctioning pressure that is dependent on the size of the pore network present within your heap or bed, and is therefore related to bed properties such as particle size distribution, particle shape, and liquid properties such as composition and temperature. In my work, it is important that I'm able to accurately simulate what goes on in a heap in the laboratory, and I will do this by making use of representative volume elements. What I mean is, I could take a cylindrical cross-section of my heap and represent it as a cylindrical column in my laboratory. Upon irrigation of my column, I would expect to get the same flow patterns as I would if my heap was irrigated under a single drip emitter point source. It is also possible to take a larger volume element such as a rectangular column, and irrigation of this column would then produce more complex flow patterns as you would get if your heap was irrigated under multiple drip irrigation point sources. To take you through my column test, I will begin by first characterizing my irrigation fluid in terms of viscosity and density. I will then be using 4 different packing materials that vary in terms of particle shape and particle size distribution, as I understand that this has an effect on the capillary suction that is present within my bed. I will then quantify this effect by conducting tracer tests using potassium chloride to generate residence time distribution curves, and these curves will then be modeled in order to obtain different hydrodynamic parameters. My current modeling approach is to make use of monoporosity, dual porosity, as well as triporosity models, with the complexity increasing as you move from left to right. For instance, your monoporosity models assume that you have a singular flow volume and that as your fluid elements flow, they undergo dispersion or mixing. Unfortunately, in certain cases, it has been found that these models are inadequate for more complex systems. Following on from that, the dual porosity models were created, which divide your volume into 2 distinct regions, your dynamic and your stagnant. An example of this is that as your fluid flows through your dynamic, it then undergoes mass transfer with a well-mixed stagnant region. Though much success has been had with these models, in certain cases they themselves have proven to be inadequate. This has led to the conceptualization of a triporosity model, in which your flow volume is divided into 3 distinct regions: your dynamic, in which dispersion occurs, a well-mixed stagnant liquid film region around your particle, as well as a linearly diffusion-controlled stagnant liquid within the particle pores. With the models in place, it is important to know that this study will make use of 4 different packing materials and 5 fluid viscosities, as well as test 8 hydrodynamic models under identical conditions, including the conceptual triporosity model. The aim is to lay the foundation for which more sophisticated hydrodynamic modeling tools can be built in order to help with better heap design, which will eventually lead to higher extraction efficiencies and the more efficient use of precious resources. And that is it, ladies and gentlemen. Thank you. I hope you enjoyed my presentation.